Hello everyone. Today I'm going to discuss yet another system software, namely MacroProcessors. This topic is incorporated in Module 1 of the syllabus. The topics that I will be going to cover are the basic concepts of macro processing, including macro definition, macro invocation, and macro expansion. Also, we will look into a simple one-pass macroprocessor algorithm, and in the process, we will also discuss certain data structures that are used in processing macros. A macro instruction, or in short, a macro, is simply a notational convenience for the programmer. In other words, macro represents a commonly used group of statements in the source program. For example, suppose that it is necessary before calling a subroutine that all contents of registers have to be saved. On a machine like SIC or SIC-XC, this would require a sequence of instructions such as STA, STB, STX, and so forth, where A, B, X, etc. are the registers available on machine SIC or SIC-XC. Now, if this process has to be repeated every time a call is done to a subroutine, then the set of statements may have to be repeated at multiple locations in the source program. So this routine work can be done using a macro. Likewise, after returning from a subroutine, suppose that it is necessary to restore the contents of all registers. So this would require a sequence of instructions such as LDA, LDB, LDX, and so forth. Again, if this has to be repeated every time after a return is done from a subroutine, then the set of statements may have to be repeated at multiple locations in the source program. So this routine work can again be done using a macro. So a macro represents a commonly used group of statements in the source program. And MacroProcessor is a system software which replaces each macro instruction with the corresponding group of source language statements. And this operation is referred to as expanding a macro. So macro instructions allow a programmer to write shorthand versions of a program and leave the mechanical details to be handled by the microprocessor. So a microprocessor's function essentially involves substitution of one group of characters or lines for another. Unlike an assembler, generally macroprocessors perform no analysis of the text it handles. In other words, the meaning of programming language statements, translation into machine language, and so forth are of no concern during macro expansion. So that way, design of microprocessors are generally machine independent. Where exactly are macros helpful? The most common use of macro is in assembly language programming. However, it can also be used in high-level language programming such as C, C++, and so forth. A common example of macro is the hash-defined statement that we use in our C programs. So now, if a programmer is allowed to take advantage of the macro feature and write the source program, before such a source program including macros is given as an input to the compiler or assembler, or in general a language translator, we need to give it as an input to the microprocessor to generate the expanded version of the source program. So basically, a macroprocessor takes as an input a source program with macros and generates the expanded version of the source program which does not have any macros, where all macro instructions have been expanded. Now, to make use of the macro feature in assembly language programming, we need to define the macro first. In our SIC or SIC-XC assembly language programming, Two macroprocessor directives, namely macro and amend, are provided to enable the definition of macros. The directive macro identifies the beginning of the macro definition, while amend marks the end of the macro definition. Now, getting back to the example of saving the register values before branching is done to the subroutine. We have already seen that we need to have a set of sequence of instructions such as STB, STA, STX, and so forth. Now, if this set of statements has to be repeatedly used in your program, first thing that we need to do is to define a macro. So as mentioned, a macro can be defined using a directive macro. The beginning of the definition is indicated with macro, while end is indicated with amend directive. So to define a macro that represents this set of instructions, we can define a macro, say, save registers. So as I mentioned, the beginning of the definition is always marked with a directive macro. The name of the macro is placed immediately preceding macro in the label field. So the symbol in the label field for the directive macro indicates the name of the macro. So in this example, we have a set of 3 instructions, that is STA, STB, and STX to be generated. So this set of statements can be now incorporated into macro definition by placing them immediately following the directive macro. So all the statements that follow macro till amend indicates the body of the macro. Actually, the body of the macro represents the set of statements that would be generated as a part of macro expansion. So once we define the macro, we may generate the set of statements that form the body of the macro by simply calling the macro with its name. So you may see after amend, we have set of instructions in the source program, and thereafter there is a reference to the name of the macro, that is save registers. So this is actually referred to as a macro instruction. So whenever a microprocessor encounters a macro instruction, it replaces the macro in this single line instruction with the statements that form the body of the macro. So in this case, the body of the macro has a set of 3 instructions, STA, STB, STX, which would be generated as a part of expansion of the line save registers. So every time this macro name is seen in the source program, the statements that form the body of the macro would be generated by the microprocessor. Now, in this example, we have seen that each set of instructions have the same operands, data 1, data 2, data 3. In the first set, the instruction STA has the operand data 1. In the second set, also, the instruction STA has the operand data 1. So what if we want to generate a sequence of instructions wherein the operands vary? For example, in this case, you may see that in the first set, the instruction STA has the operand data 1, while in the second set, the operand is data 4. Likewise, the instruction STB has the operand data 2 in the first set, while in the second set, it is data 5. So now, in order to generate instructions of this kind, we need to define a macro which has parameters. So I could define a macro wherein the body of the macro includes instruction STA, STB, STX, but the operands are indicated by variables, what are known as macro parameters, as shown here. So this slide shows definition of a macro, namely store registers indicated with strg. As usual, the beginning of the macro definition is indicated with the directive macro, and following the instruction macro directive macro, we have a set of 3 statements, STA, STB, STX, which is something that we want to generate in the source program. And as you see, in the first set, STA has the operand data 1, while in the second set, we have the operand data 4. So while you incorporate this into the body of the macro, the operand is indicated by a parameter P1. Likewise, the second instruction is indicated by STB, while the operand is data 1 in the first set and data 5 in the second set. So again, this instruction is placed as the second instruction in the body of the macro with the operand indicated with the parameter P2. Likewise, the third instruction in the set is STX, and we place this as a third instruction in the body of the macro with the operand being the parameter P3. So P1, P2 and P3 are the parameters, and we have defined a macro with parameters, unlike in the previous example wherein the macro was defined without any parameters. All macro parameters are identified with the symbol ampersand. And all parameters should be listed immediately following the directive macro. So all parameters that are placed in the operand field of the directive macro indicates the macro parameters. So this ampersand identifies that the symbol that follows is a macro parameter and not a normal label or a normal symbolic operand. And it also facilitates the substitution of arguments to enable generation of instructions with different operands. So now, having defined the macro strg, now if we want to generate this set of statements, then we need to invoke this macro with the name. However, unlike in the previous example, here you also need to specify the argument values that has to be substituted for the parameters P1, P2 and P3. For example, we have here the first macro instruction strg with a list of arguments data 1, data 2, data 3. So whenever a microprocessor encounters this instruction referring to the macro, namely strg, it generates the statements that form the body of the macro with the parameter P1, which is the first parameter in the parameter list, being substituted with the first argument in the argument list, that is data 1. Likewise, occurrence of P2 is replaced with the argument data 2 and P3 will be replaced with data 3. Thereby, this instruction would be expanded into STA data 1, STB data 2 and STX data 3. Now, if the same macro is invoked or called with another set of arguments, say data 4, data 5, data 6, then the set of statements generated would be STA data 4, because data 4 is the first argument and it would be replaced with the first parameter P1. Likewise, the remaining statements generated would be STB data 5 and STX data 6 respectively, with parameter P2 replaced with data 5 and P3 replaced with data 6. So this is an example of a macro which is defined with parameters. And it enables the statements that form the body of the macro to be generated with different operands. So as you have just seen, the symbol in the label field of the directive macro is the name of the macro. So in this example, strg is the name of the macro. The entries in the operand field after the macro directive indicates the parameters of the macro instruction. So P1, P2, P3 in this example are macro parameters. And as I mentioned, every macro parameter is distinguished from a symbolic operand with the symbol and. And also this ampersand enables substitution of parameters during macro expansion. As you see, it enables P1 to be replaced with the argument data1 in the case of first invocation or the case of first instruction here. Likewise, P2 would be substituted with data2 and P3 would be substituted with data3. The name of the macro along with the parameters define a pattern named as a prototype for macro instructions. All the statements that follow the directive macro till end is referred to as a body of the macro, and as I mentioned, these are statements that will be generated as a part of macro expansion. So in general, a macro would be defined as shown here. In the symbol field, we have the name of the macro. Following it, we have the beginning of the macro definition identified with the keyword or the assembler macroprocessor directive macro. Following the directive macro, we have a list of parameters which enable substitution during the expansion. Statements that follow the directive macro till end forms the body of the macro. So in the first example that we have defined, this shows a macro without any parameters. It's a non-parameterized macro definition. The name of the macro is save registers, and there are no parameters as you see immediately following the directive macro. There are the statement that form the body of the macro is indicated with store instructions, STA, STB, STX. And you can invoke this macro by just the name. You don't have to specify any values as arguments because this is a macro which without any parameters. So every occurrence of save registers would be replaced with statements STA data1, STB data2 and STX data3. Note that operands, same set of operands will be used every time the macro is called. The same macro could be defined with parameters such that in the place of data1, data2, data3, we can use parameters P1, P2, P3. So this enables P1, P2, P3 to be replaced with different values depending on how this macro is invoked or referred to in the source program. For example, when we call this macro strg with data1, data2, data3 as arguments, P1 would be replaced with data1, P2 would be replaced with data2 and P3 would be replaced with data3. Likewise, if you call the same macro strg using arguments data4, data5, data6, then P1 would be replaced with data4, P2 would be replaced with data5 and P3 would be replaced with data6. So please note the macro parameters should be listed immediately following the directive macro, and it has to be listed in the operand field for the instruction. So the statement that we have seen here, that is strg data1, data2, data3. Likewise, the statement strg data4, data5, data6, which makes a reference to a macro that is defined earlier, is called as a macro call. So in the earlier example, you may see that the macro here is called by just using the name because the macro doesn't have any parameters. While in the next example, you may see that the macro is invoked again with the name, but following the name, we specify the values that has to be replaced for the parameters P1, P2, P3. So this statement is referred to as a macro invocation statement or a macro call. This is similar to a function call. You may see that in a language like say we call a function with the name of the function and we also pass arguments that has to be used. Similarly here we invoke a macro with the name And following the name, you need to specify the list of arguments that has to be substituted for the parameters. So syntax is macro name followed by a space followed by list of arguments. So here A1, A2, etc. are the arguments. So we have n arguments here, which has to be substituted for the parameters in the macro definition. Whenever a macro invocation statement is encountered by a macroprocessor, it will be expanded by replacing the corresponding statement with statements that form the body of the macro. And all macro parameters will be replaced with the arguments based on the position. That is, the arguments and parameters are associated with one another according to the position. That is, first argument corresponds to first parameter in the macro prototype. Second argument corresponds to the second parameter in the prototype, and so on. Remember, we use the term parameters to refer to the names that are used immediately following the directive macro. That is, in macro definition, whatever names are used and the names that follow the symbol ampersand are referred to as macro parameters. Okay, and the symbols that we use in the macro invocation, that is here, are referred to as macro arguments. So data 1, data 2, data 3 are the arguments. P1, P2, P3 are the parameters. Arguments are associated with parameters by position. Data 1 is the first argument which corresponds to first parameter P1. Likewise, data 2 is the second argument which corresponds to second parameter P2. Similarly, data 3 is the third argument and it corresponds to the third parameter P3. So replacement of or substitution of parameters with arguments will be done based on the position. So as I mentioned, this is an example of a macro without parameters, and likewise the macro call doesn't have any arguments. While this macro invocation statement is encountered or when it is read by a macroprocessor, it replaces this statement with statements that form the body of the macro. In this case, the body of the macro has the three instructions: STA data 1, STB data 2, and STX data 3. Again, second reference to or second macro invocation save registers again generates the same set of statements: STA data 1, STB data 2, and STX data 3. So same macro has been written using parameters P1, P2, P3, and it is being invoked with the name strg, and following that we have arguments data 1, data 2, data 3. A second call to the same macro is done with different set of arguments data 4, data 5, data 6, and we can see the expansion that is generated for the first macro invocation here in the expanded source. You may see that the set of statements generated are STA, STB, STX, with P1 replaced with data 1, P2 replaced with data 2, and P3 replaced with data 3. Likewise, for the second macro invocation or macro call, the statements generated or the expanded set of statements are STA, STB, STX with operands respectively data 4, data 5, data 6, which have been replaced for the parameters P1, P2, P3 respectively. So one point needs to be paid attention during the expansion of macros or a macro instruction. That is the comment lines within the body of the macro. Generally, when a macro invocation statement is expanded by substituting the line with the statements that form the body of the macro, all comment lines will be deleted. So any comment lines that form the body of the macro definition will be simply ignored, or it will not be written into the expanded file. However, the macro invocation statement itself will be written into the expanded file as a comment line. So this line will be generated as a part of macro expansion, and it will be indicated as a comment line with the dot ahead of it. Now, if there are any labels on the macro invocation statement, if we have any label here, then it will also be retained on the first statement that is generated in the macro expansion. So this is the expanded source which is shown with the macro invocation statement being written to the expanded file as a comment. So please note, in the assembly language programming, we indicate comment with the dot. So please note, before strg data1, data2, data3 is expanded with the set of statement sta, stb, stx, the invocation statement itself is written to the expanded file as a comment line. However, when this statement is processed by a language translator such as assembler, the comment line would be simply ignored. Now let us see the difference between a macro and a procedure, or a macro call and a procedure call. Generally, whenever a macro call is encountered by a microprocessor, every macro invocation or macro call would be replaced with the statements that form the body of the macro. That is, statements that form the body of the macro will be generated for every time a macro is expanded. For example, here we have two macro calls. For every call, the statements that form the body of the macro will be generated. You may see that for the first call, we have one set of 3 statements generated. Again, for the second call, another set of 3 statements will be generated. This is not the case with the procedure calls. Statements in a procedure or a subroutine will appear in the source file only once, regardless of how many times it is being called. So this is the case with the functions as well in high-level language programs. So the major difference is statements that form the body of the macro is generated every time a macro invocation statement is expanded, while the statements in the subroutine will appear only once, regardless of how many times a subroutine or a procedure is called. So during the expansion of a macro, one point needs special attention, that is the use of labels in the macro definitions. Now, we have already seen that once a macro is defined, the same macro can be invoked at multiple places in the source program. And every time that macro is invoked using a macro invocation statement, the macro invocation statement will be replaced with statements that form the body of the macro. So if same macro is invoked at multiple points in the source program, every time the macro call or macro invocation statement is expanded, the same set of statements will be generated at multiple points in the source program. So if the body of the macro includes a label, this leads to the generation of duplicate labels. And you already know that duplicate labels are not allowed in the source program and are treated as errors by the assemblers. So the solution is try to avoid the labels in the body of the macro in a usual way and make use of some sort of relative addressing to refer to an instruction and avoid labels as far as possible. In order to understand this, we will take a macro, namely rdbuff, which is parameterized, which has a single parameter, namely indeb. So rdrec is a macro which is used to read records from an input device into some memory locations. So please note the macro is named rdrec and it has one parameter, namely indeb. The statements that form the body of the macro are shown in the rectangle here. There are a few statements immediately following the directive macro, and thereafter we have two instructions which involve a label. The first instruction is td equals x ampersand indv. Now please note the instruction td tests if the device that is specified in the operand field is ready or not to send or receive a data. The following instruction, as a result of the test, condition code flags are set And the following instruction examines the condition code flags to see if the condition code flag is set to equal. If so, it branches to the same instruction, that is TD, loops back to the location where the instruction TD is placed and repeatedly tests. So basically, if the device is not ready, we need to keep on testing until the device becomes ready. So you may see that there is a looping here. So the instruction TD is indicated with a label loop, and the following instruction makes a reference to this particular symbol loop. So what happens, so the macro definition has two statements here, including certain other statements which are not of importance here. So what happens when this macro rdirect is being invoked with an argument, say f1. We have called the macro here, we have one macro invocation, namely rdirect f1, and the same macro is invoked with another argument f2 at some different point of the source program. So as you know, whenever a macro is invoked, statements forming the body of the macro will be generated as a part of macro expansion with parameters replaced with arguments. So basically, for the first macro invocation, INDEV would be replaced with F1. And during the second invocation, INDEV would be replaced with F2. So the expansion for the first macro call is shown in the right hand side. Please note the first line here indicates the macro invocation itself indicated as a comment line. As I mentioned, when the expansion is done, the macro invocation statement itself is written to the expanded file as a comment. After this, statements that form the body of the macro are generated. Please note the parameter INDEV is replaced with F1 because we have an argument immediately following the macro name. And the second statement is generated, that is JEQ loop. Please notice that we have a label here, that is loop, that is generated as a part of macro expansion. Now, what would be the expansion corresponding to the second macro invocation statement rdirect f2? So again, this is shown here in the right hand side in that as a part of the expanded file. The macro invocation statement is written as a comment, and the statements that form the body of the macro is again generated. Now, if you look into this source program, you may see that loop appears at two places, meaning that it is a duplicate label, which is not allowed in assembly language programming. A same label cannot appear in the source program at 2 points. Now, the dilemma is when you have an instruction like JEQ loop, whether to branch to this location or to this location is not known. That is why duplicate labels are not allowed in assembly language program. So this could be avoided, as I mentioned, by making use of some sort of relative addressing. So please note, the instruction here indicates that if the device is not ready, branch back to the location loop. You can rewrite the same set of statements using in the place of the operand loop, you could use star -3. What does star mean? Star indicates the current location counter value. So current location counter value -3 indicates a branching back to the location where the instruction TD is placed. So assume at the location counter for the instruction TD is 1000. So since TD is a 3-byte instruction, the next address, the address corresponding to JEQ would be 1003. So 1003 -3 would be referring to the location 1000, which has the instruction TD. So you can avoid a label and write the same instruction using star -3 as the operand in the place of loop. Now we shall see how the expansion takes place when this macro is invoked with the macro invocation statement rdirect f1. Please note the statements that form the body of the macro will be generated as a part of expansion. The first statement after dots is TD, and the parameter INDEV is replaced with F1 because F1 is the argument that corresponds to INDEV here. The second statement generated would be JEQ star -3. So star minus 3 here represents the instruction preceding JEQ. Now, the expansion corresponding to the second statement is shown in the right hand side again. The macro invocation statement is rdirect f2. F2 is the argument which has to be substituted for the parameter I and DEV. Please note the line, the macro invocation statement is added to the expanded file as a comment, and the statements forming the body of the macro are generated here. So I and DEV is a parameter which is replaced with the argument f2. The second statement generated is JEQ star minus 3. So please note we have not used any labels here, and there is no dilemma regarding the branching in the case of the first set of two instructions. The JEQ star minus 3 obviously refer to the first TD instruction, and in the second case JEQ star minus 3 refers to the second TD instruction. So assume if TD had an address 1000, JEQ would have the address 1003. So JEQ star minus 3 would refer to the location 1003 minus 3, which is 1000, which is this instruction TD equals X F1. Likewise, assume that the address at the location TD equals to X F2 is say 2000. So the next instruction would have the address 2003. So JEQ star minus 3, star indicates the current location counter value. So at this point, if the location counter is 2003, 2003 minus 3 would refer to the instruction TD equals XF2, not to the instruction TD equals to XF1. So that way we can avoid generation of duplicate labels by making use of relative addressing, although this is not an efficient technique. So this particular slide shows an example of a macro being defined. The program is named copy, and it defines a macro, namely rdbuff. The name of the macro is rdbuff, which has three parameters: device address, buffer address, and record length. The following three lines are the comment lines, and we have a set of instructions starting with clearx to stx ampersand record length, and end of the macro definition is identified with the directive amend. So the statement starting from the comment till amend indicates the body of the macro. Parameters are INDV, buffer address, and record length, and the name of the macro is rdbuff. Following this, we have another macro defined, namely wrbuff. The function is to write the records from the buffer into an output device. So the name of the macro is wrbuff, and the parameters are output device address, buffer address from where the records have to be read, and the record length, the length of the record that has to be written to the output device. So please note, here we have used a relative addressing to avoid the use of labels in the body of the macro. So JEQ star minus 3 corresponds to the branches to the location where the instruction TD is placed. Likewise, you can calculate and see where JEQ branches to and where JLT branches to. Similarly, in the macro wrbuff, this is a macro wrbuff being defined. The first three lines are the comment lines, and the body goes on till the directive amend. Again here, labels have been avoided by making use of relative addressing. So the main program starts here. Please note, the program begins at this point. Start indicates the beginning of the assembly language programming. Immediately after that, we have a macro, namely rdbuff defined. Following that, we have a macro, namely wrbuff defined. Next, the first instruction that is not part of the macro is actually beginning here with the statement first STL return address, which is the main program. The second statement is a macro invocation statement. Here, please note, the macro invocations is indicated in the opcode field with the macro name. The macro name here is rdbuff. Rdbuff was already defined here. Okay, so this particular statement indicates a macro call or a macro invocation, and the parameters have to be replaced with arguments. The first parameter has to be replaced with argument f1. Second parameter should be replaced with buffer, and the third has to be replaced with length. Please note the macro call indicates or refers to the macro rdbuff, and the arguments to be used are f1, buffer, and length. This particular slide has two more macro invocations, and the subsequent invocations are to the macro wrbuff. You may see that the macro wrbuff is invoked at two places, at line number 210 and line number 220. The first macro invocation uses the arguments 5, buffer, and length, while the second uses arguments 5, EOF, and 3. 05 indicates the output device address, buffer indicates the address of the memory location from where the reading has to be done, and length indicates the record length. So in this particular slide, you can see that there are three macro invocations. The first invocation invokes the macro rdbuff, and the subsequent two invocations invokes the macro wrbuff. Each of these invocations are followed or has three arguments which has to be replaced with the corresponding three parameters that have been used in defining the macro, that is shown in each of the slides here. The three parameters for rdbuff are INDEV, buffer address, and record length, while for wrbuff it is output device address, buffer address, and record length. So this is an expanded version of the source program. You can go through the slide and see how the expansion takes place. So just getting back, so this is the first instruction after the macros are defined. First STL RET which is generated in the expanded file. Following that, we have a macro call, namely rdbuff, f1, buffer, and length. F1 is to be substituted for INDEV, buffer has to be substituted for buffer address, and length has to be substituted for record length. Please note, this macro invocation statement has a label. So this label will be placed, or this will be retained as a label to the first statement that is generated as a part of macro expansion for the macro rdbuff, which is the first statement in the macro rdbuff. If you just go back, the first statement is clear X. All of these are comment lines which will not be appearing as a part of the macro expansion. So the first statement generated as a part of macro expansion for rdbuff is clear X. So I am showing the expansion here. So please note, the macro invocation statement itself is generated as a comment line here, which is underlined. Following that, statements following the body of the macro rdbuff has to be generated. We have first three lines which are comment lines which are ignored. Then the statements generated are clear X, clear A, clear S, and this will go on till LDT hash 4096. When TD is generated, INDEV is replaced with the macro argument F1. So the statements generated are clear X, clear A, clear S, LDT hash 4096, TD followed by the operand where parameter INDEV is replaced with F1. Also please note, C loop is a label which will be retained as a label for the first instruction that is expanded as a part of macro expansion for the macro rdbuff. Macro expansion for the macro invocation statement rdbuff. F1, buffer, and length. Likewise, rest of the statements are generated with INDEV replaced with F1, buffer address being replaced with buffer, and record length replaced with length. So last statement in the definition is STX record length. So this is the last line that is generated. You can see it is highlighted here in a rectangular box. Last instruction is STX, and in the definition you may see that the parameter is record length, which has been replaced with length here. So following this, just go back to the original source program. After this, Next we have an invocation, after this macro call, the next set of statements are LDA length, come, hash 0 and JAQ and fill. So the statements generated after the macro RDBuff is expanded is LDA length, come, hash 0, JAQ and fill. So these are part of source program which are written to the expanded file as such. So following this, we have another macro invocation wrbuff 05 buffer length. Now this statement is a macro call, so this has to be replaced with the statements that form the body of the macro wrbuff. So wrbuff is defined here, which has a set of statements initially beginning with the comment lines. Following the first statement is clearx. So all lines from clearx till JLT star minus 14 will be generated as a part of macro expansion. These lines will be ignored because these are comment lines. So we will see the expansion for the macro invocation wrbuff 05, sorry, it's not the second one, wrbuff 05 buffer length. So the statements generated will be from clearx to JLT star minus 14. So we will just look into it here. Please note this is the second expansion corresponding to the macro invocation wrbuff 05 buffer length. As you see here, the line itself is written to the expanded file as a comment line. I have underlined it here. And the statements generated are from clearx to JLT star minus 14 as I mentioned. The device address is replaced with 05. Buffer address is replaced with buffer, and record length is replaced with length, as you can see. If you just go back, record length should be replaced with length, buffer address should be replaced with buffer, and output device address should be replaced with 05. So now again going back to the source program, after this line is expanded, we have one source language statement JC loop, which will be generated immediately after, that is in line number 215, you can see it. Line number 210 to 210H indicates the expansion of the macro wrbuff. Okay, so after that we have JC loop in the source program, which will be generated as such. Following statement in line 220 is again a macro invocation statement, which again invokes the macro wrbuff, but with the arguments 5, EOF and 3. Please note this particular statement has a label which has to be generated or retained in the expanded file as a label for the first statement of the expanded macro wrbuff. So we will look into it now. So after JC loop, we may see that the macro invocation itself is written as a comment line, and I have highlighted it in the blue rectangle. The following statement should indicate the expansions of the macro wrbuff. So we can see it here. Clearx is the first statement. I'm going back again to show the macro RDBuff. The first statement is clearx, last statement is JLT minus 14. Now record length has to be replaced with 3. Output device outdiv has to be replaced with 05, and record length has to be replaced with 3. Likewise, buffer address here needs to be replaced with the second argument, that is EOF. So the expansion is nfill clearx, which starts at line number 220A and goes on till 220H. The last instruction is JLT star minus 14. Record length has been replaced with 3. Buffer address has been replaced with EOF, and the device address has been replaced with 05. Now getting back to the source program, we were at this point. After that, we have a set of instructions starting with jump at return address and goes on till buffer reserve byte 4096. So all those statements will be generated in a normal way and written to the expanded file. So you may see it here. All remaining statements indicate the source language statements written as such to the expanded file, and last statement written is the end first. So basically all statements which are not a part of macro definition or expansion or macro invocation are written as such to the expanded file, starting from the start statement. Starting from here, all lines are expanded. Whenever there is a macro call, this will be replaced with the statements that form the body of the macro. And while this is done, all parameters will be replaced with the corresponding arguments. So this has to be done for every macro invocation statement. You may see that in this source program, we have 3 macro invocations which are shown in rectangular, and the expansion is shown here in the rectangular boxes. And they have been color coded. RDBuff is color coded with a kind of orange box, and WRBuff has been subsequently shown at 2 locations with a blue rectangular box, as you see here. I suggest that you go through the source program and generate the object program by hand to understand how the macro expansion takes place for this particular program. This is the same example that was discussed in the textbook. If you have any queries, you can get back through Canvas. Now, we have already seen how a macro is defined and how a macro invocation statement gets replaced with the statements that form the body of the macro. So MacroProcessor processes the macro invocation statement by replacing it with the statements that form the body of the macro. So whenever a source program is given as an input to the macroprocessor, whenever a source code with macro is given as an input to the macroprocessor, the function involves generating the expanded version of the program. In generating the expanded version of the program, the macroprocessor has to accomplish these 4 functions. The first thing is it has to recognize a macro definition. You know that in assembly language program, macro definitions are identified with the keyword macro and mn. So basically your macroprocessor will have to identify if there is a directive macro, and it has to define the macro somewhere so that when a macro call is encountered, the macro definition could be used in expansion. So one of the function of the macroprocessor is to recognize the macro definition, which is generally identified with keywords macro and mn. The macro being identified has to be saved. Why the macro has to be saved? Because when that macro is referred by a macro invocation statement, statements that form the body of the macro has to be generated. So macro has to be saved somewhere. Every macro in a source program has to be saved. Remember, in the example that we have just seen, there are 3 macros. There are 2 macros. One is RDBuff and the other is WRBuff. So each of these 2 macros will have to be saved. And it is important to know which set of statements correspond to which macro. For example, WRBuff, as a part of WRBuff, we have instructions clear x to JLT star minus 14. While statements that form the body of the macro RDBuff is clear x to STX record length. So it's important that whenever a macro processor encounters a macro definition identified with the keyword macro and mn, it saves it so that the statements that form the body of the macro could be used later during the expansion. The third function of the macroprocessor is to recognize the macro calls. So how are macro calls recognized? If you just go back, I have indicated a macro call here in this particular slide. Remember, macro calls are all identified with macro names appearing in the place of the opcode. So if the opcode is a macro name, it indicates a macro call. So we have RDBuff, WRBuff, which appears in the opcode field, which means that it is a macro call. So macroprocessor needs to identify the macro calls which are referred with the macro names. So whenever a macro call is encountered, what is to be done? Macroprocessors will have to replace that macro call with the statements that form the body of the corresponding macro. So the fourth function of the macroprocessor is to expand the macro calls or replace macro invocation statements or macro calls with the statements that form the body of the macro. So these are the four functions. First is recognizing the macro definition. Recognition happens using a directive macro and amend. Save the definition, that is all statements that form the body of the macro has to be saved somewhere. Third function is recognizing the macro calls. Recognition of macro calls happens with the name appearing in the opcode field. And the last function is expanding. So whenever MacroProcessor recognizes that a macro call is encountered, it has to replace that macro call with statements that form the body of the macro. Remember, macro call is identified with the macro name and argument list. So statements that form the body of the corresponding macro has to be expanded. Now, coming to the implementation of microprocessors, we have seen how to implement an assembler, and you have seen that assemblers can be implemented as one-pass assembler, two-pass assembler, multi-pass assemblers, and so on. Likewise, a macroprocessor can be implemented as a two-pass macroprocessor or a one-pass macroprocessor. A two-pass macroprocessor is one wherein all macro definitions are processed during first pass, and all macro invocation statements are expanded during the second pass. So just as we have assemblers, a two-pass assembler which defines all symbols in the first pass and generates all object codes in the second pass, likewise a two-pass macroprocessor is one which processes all macro definitions in first pass and which processes all macro invocation statements during the second pass. Now, it's possible that one macro definition is nested within another, or you can contain one macro definition inside of another macro, as you see in this particular slide. So here you may see that the outermost macro here is named macro S. So basically this defines a macro for the standard version of SIC. And the outer macro contains two macros being defined inside. One is rdbuff and the other is wrbuff. As you know, rdbuff is a macro which reads the records from a device, namely INDV, from the input device. Likewise, wrbuff is a macro which writes the record from the memory location, namely buffer, from the buffer to the output device. So the inner macro here represents or includes the statements for rdbuff for the standard version of SIC. Likewise, the inner macro wrbuff includes the SIC instructions for writing the records from the buffer into the output device. So you have here the outermost macro, macro S, and the two inner macros, rdbuff and wrbuff. You may see that the outer macro includes definition of two macros, rdbuff and wrbuff, which is written for the standard version of SIC. Likewise, I have another macro, nested macro here, wherein outermost macro is macro X, and we have two inner macros, rdbuff and wrbuff, which accomplishes the task of reading records and writing records with the instructions written for SIC XC. Now, if you want to use rdbuff or wrbuff for the standard version, then you can invoke the macro S. While if you want to use macro rdbuff and wrbuff for SIC XC instruction, then you could invoke the macro X. Please note, the outer macro is not parameterized, only the inner ones are parameterized here. Likewise, in case of the second one, that is the macro written for SIC XC, the outer macro is not parameterized, only the inner ones are parameterized. So as I mentioned, macro S contains definitions of rdbuff and wrbuff for SIC instructions, and macro S contains definitions of rdbuff and wrbuff for SIC XC instructions. Now, if a program that is to be run on SIC system wants to use rdbuff or wrbuff, then it can invoke the macro S. Whereas if the program is to be run on SICHC, then it can invoke the macro X. One point that needs to be noted here is when we define the macro S or macro X, the inner macro need not be defined. Defining the outer macro does not mean that the inner macro is defined. So definitions, defining macro S or defining macro X does not define RDBuff and WRBuff. The inner macros are defined only when outer macros are expanded. That is, when macro S is expanded, RDBuff and WRBuff for macro S will be defined. Likewise, when macro X is expanded, when the macro invocation statement for macro S is expanded, RDBuff and WRBuff corresponding to macro X would be defined. So this means that in a 2-pass macroprocessor, as I mentioned earlier, all macros have to be defined in pass 1 and all expansions will be done in pass 2. So what happens with nested macros in case of 2-pass macroprocessors is, unless the outer macro is expanded, the inner macros are not defined. So in a 2-pass macroprocessor, since the expansion happens in the second pass, inner macros will never be defined. So that is one of the shortcoming or drawback of a 2-pass macroprocessor, because macros have to be defined in first pass. So when you have nested macros, unless the outer macro is expanded, which happens in the second pass, the inner macros will not be defined. So the problem is with respect to the definitions of inner macros whenever one macro is nested within another. So alternative is to use a 1-pass macroprocessor. A 1-pass macroprocessor is one which is able to alternate between macro definition and macro expansion in a single pass. Such a macroprocessor is able to handle macro inside a macro. The only restriction with 1-pass macroprocessor is that all macros have to be defined in the source program before they are invoked. So all macro definitions should appear in the source program before macro statements or macro invocation statements appear in the source program. So in order to assist in macro expansion or in processing macros, 3 data structures are used by 1-pass macroprocessor algorithm. The first one is a definition table. The definition table is used to store the macro definition or to save the macro definition, including macro prototype and macro body. So as I mentioned earlier, there are 4 functions of a macroprocessor: recognizing the macro definition, save that macro definition, recognize the macro call, and save the macro call. So whenever a macro definition is encountered, the macro statements that form the body of the macro along with the prototype needs to be saved. So the data structure that is used for saving the macro definition is referred to as a definition table. So definition table is a data structure which stores the macro definition, including macro body and prototype. So since comments are not a part of macro expansion, when the definitions are saved, comment lines will be omitted. That is, comment lines will not be entered into the definition table. Again, when the statements that form the body of the macro are saved into the definition table, all parameters are replaced with positional notations. The positional notation is of the form $n, where n indicates the position of the parameter in the parameter list. So this is done. So every parameter is replaced with the positional notation of the form $n, where n indicates the position of the parameter in the parameter list. This is done to enable substitution of arguments based on the position, because you have already seen first parameter will be replaced with first argument. So whenever you see a parameter in the body of the macro, if it happens to be the first parameter, you have to replace it with $1. So if it is a third parameter, you have to replace it with $n and so forth. The second data structure used by 1-pass macroprocessor is a name table. So whenever you store a definition into the definition table, remember definitions are all identified with the macroprocessor directive macro. So whenever you place the macro definitions into the definition table, the name of that macro should be stored into the name table. So basically, name table serves as an index to the definition table. Entries in the name table serves as an index to the entries in the definition table. So you place the macro definition into the definition table, and the macro names should be saved into the name table. Also, the macro name table contains 2 pointers identifying the beginning and end of the macro definition that is kept in the definition table. Corresponding to each macro name, there are 2 pointers, one indicating the beginning of the corresponding macro and another indicating the end of the macro in the definition table. The third data structure is the argument table, and it is used generally during the expansion of a macro. So whenever a macro invocation statement is recognized, all arguments following the macro name has to be stored into the argument table in the order of their position. That is, the first argument has to be placed as a first entry in the argument table, second argument has to be placed as second entry, and so forth. So when a macro invocation statement is encountered, argument table has to be first set up, then the macro invocation statement has to be expanded. So as a macro is expanded, the arguments from the argument table will be substituted for the corresponding parameters which are indicated in the body of the macro as positional notations. So for example, if you have question mark 3 in the body of the macro, this will be replaced with the third argument in the argument table. So we will take an example and understand how the data structures are actually created and used in expanding the macro or processing the macro. We will consider a source program which defines a macro, namely add numbers, and the function of the macro is to add 2 numbers accomplished using a sequence of instruction LDA, add, and STA. The first instruction LDA loads the first value into register A indicated in the operand field. The second instruction adds the content adds the content of register A with the second operand, and the third instruction STA stores the result into the destination location indicated in the operand. So it's a very simple macro which accomplishes the task of adding 2 numbers and storing the result in a memory location indicated by the third operand. The source program has certain other statements which are indicated with the dotted lines, which are not of direct concern here as far as macro processing is concerned. So I have indicated them using dotted lines. The macro is invoked. As you know, we invoke a macro with the name. So add numbers is the name of the macro. We invoke the macro, and following the macro name, you have to specify the list of arguments that has to be used in substituting the parameters during the expansion of the macro. So we have in the first invocation a list of 3 arguments, data 1, data 2, and sum, which has to be accordingly substituted for P1, P2, and P3 respectively. The second invocation again refers to the macro add numbers, and the arguments this time are num1, num2, and result. Num1 will be replaced for P1, num2 substituted for P2, and result substituted in the place of P3. So add numbers is the name of the macro. Body has 3 instructions. Parameters are P1, P2, P3. And we have 2 macro invocations referring the macro add numbers. This is a macro definition. So as I mentioned, arguments are associated with parameters by position. Data 1 corresponds to P1, data 2 corresponds to P2, and sum corresponds to P3. Likewise, in the second invocation to the macro add numbers, num1 corresponds to P1, num2 corresponds to P2, and result corresponds to P3. So we shall see the use of 3 data structures, that is the name table, definition table, and argument table in processing this source program. So I have shown the segment of the source program here at the top right corner. and I have two data structures, name table and the definition table. As I mentioned, definition table stores the macro definitions. Name table holds the name of the macro that is defined in the definition table with two pointers to the beginning and end of the definition that is kept in the definition table. Now we shall see the source program that I have just explained for adding two numbers. So the arrow here indicates the statement in the source program that is being processed. So we begin starting from the start statement. So we don't have any start statement here. I have not indicated it as such here. So the statements that are indicated in dotted lines indicates the source program statements which are processed one after the other. So after the dotted lines will be actually generated to the expanded file as such. The next statement processed is add numbers macro ampersand P1, P2 and P3. Please note this particular instruction indicates a macro definition because we have a directive macro in the opcode field. The name of the macro is indicated in the operand field add numbers, and there are three parameters P1, P2, P3 which are indicated in the operand field. So now when this instruction is encountered by the macroprocessor knows that it is a macro definition because it is indicated with the directive macro. So whenever a macro definition is encountered, the function of the macroprocessor is to save the definition, save the statements that follows or that represents the body along with the prototype. So I have shown it in the next slide here. Please note the name of the macro and the parameters which form the prototype is entered as a first line into the definition table. The dotted lines in the definition table shows other entries that have been made as a part of macro definition corresponding to the source program, which are not shown here. So while we process add numbers, macro and P1, P2, the entry made into the definition table is the name and the parameters which indicate the prototype, which actually define the pattern for the macro instruction. So this is the first line that is entered into the definition table. Also, the name of the macro should be entered into the name table. So add numbers has been entered into the name table. The first column here indicates the name of the macro. So this indicates the beginning. So the immediate next slide shows a pointer being kept in the name table indicating the beginning of the macro definition add numbers corresponding to the entry add numbers. So we have initially entered add numbers into the name table. The corresponding definition had been entered into the definition table, that is a prototype has been added, add numbers with parameters. Following that, a pointer is kept in the name table indicating the beginning of the definition in the definition table. So after that, the execution proceeds with the next line, that is LDA and P1. So please note, entry into the definition table or saving of the macro definition has to go on till the directive end is reached. So the next statement that we have read is LDA and P1. This is not end directive, so it is not end of the macro definition. So line will be entered into the definition table, but before this line is entered, parameter has to be replaced with the positional notation. This is the first parameter in the list, so this has to be replaced with question mark 1. The general form is question mark n, where n indicates the position of the parameter. Now P1 is the first parameter in the parameter list, so the statement generated or saved into the definition table is LDA followed by question mark 1. So this is the entry, this shows the status of the definition table after the first statement in the body of the macro is processed. Moving, okay. Please note, we got question mark 1 here because P1 is the first argument in the first parameter in the parameter list. Proceeding ahead, the next statement is add ampersand P2. Now this is again a statement that indicates the body, and we have not yet reached the end directive. So this line need also be saved into the definition table with the parameter replaced with the positional notation. P2 is the second parameter, so we enter the line add into the definition table with P2 replaced with question mark 2. It is 2 because P2 is a second parameter. Proceeding ahead, the next statement is STA ampersand P3. So now this is again a statement indicating the body of the macro. We have not yet reached the end of the macro definition. So this line needs to be entered into the definition table. So STA is entered and P3 is a parameter. We have an ampersand sign indicating that the argument is the operand is a parameter. So P3 has to be now replaced with the position indicating the parameters position in the parameter list. So in the parameter list, P3 is the third one. So we have to enter STA question mark 3. The next statement that is processed is emend in the source file. So now that the end directive is encountered, this is entered into the definition table indicating the end of the definition of the macro add numbers. So when the end is reached, the pointer is set in the name table indicating the end of the macro, namely add numbers. So we set a pointer or place a pointer to the end of the macro definition in the definition table for add numbers. Next, the execution proceeds ahead with the next set of statements. So we have indicated it with the dotted lines. So those lines will also be read from the source file and processed. So the next statement will be add numbers data1, data2 sum. Now, this is a statement that invokes the macro which is already defined in the definition table. So please note, this is not a macro definition or this is not any normal assembly language statement. This is a macro invocation. So how do we recognize a macro invocation? All macro invocations have in the opcode field the name of the macro which is already entered in the name table. So if the opcode field has a name which is already present in the name table, it means that it is a macro which is already defined. So it is also indicating a macro invocation statement. So you need to replace this statement with the statements that are saved in the definition table with all positional notations replaced with the corresponding arguments that are following the name add numbers. So when this statement is processed, the macroprocessor sets up, so it knows that this is a macro call because the opcode has a name add numbers which is stored in the name table. So this is identified as a macro call, and the macroprocessor sets up an argument table by keeping all arguments in the argument list following the macro name in the order of its position. First argument is data1, which will be placed as a first entry in the argument table. The second one is data2, which is saved as second entry, and the third is sum. So the argument table setup for this macro invocation add numbers data1, data2, and sum is as shown in the argument table here. Note that we keep it in the order of its position because it allows the substitution of parameters that is indicated with the positional notation. For example, question mark 1 will be replaced with data 1, 2 would be replaced with data 2, 3 will be replaced with sum. So I have indicated it clearly here. While we save the definition, we have used positional notation. When a macro call is encountered, arguments table is set up in the order of the position of arguments. So this allows the macro add numbers data1, data2, sum to be replaced with a set of statements LDA, add, STA, with question mark 1 replaced with data1, question mark 2 replaced with data2, and 3 replaced with sum. Now proceeding ahead, after that we have a set of source language statements, and thereafter we have another macro invocation add numbers num1, num2 result. So again, we know that this is a macro call because the opcode has a name which is present in the name table. So this indicates a macro call. So argument table has to be set up. So argument table is set up with arguments num1, num2 result in the order of their position. So first argument is entered as a first entry into the argument table. The second num2 is entered as a second entry and thereafter result. So this is the argument table set up for add numbers corresponding to the second invocation. And as you see, first the position rotation 1 will be replaced with num1, 2 replaced with num2, and 3 replaced with result. We shall now look into the data structures that are created for the macros that are defined or invoked in the program copy. The program defines a macro, namely rdbuff, at line 10. The parameters are inrep, buffer address, and record length. The body of the macro includes lines from line number 15 to 95. The first three lines, that is line number 15, 20, and 25, are comment lines and are generally not saved into the definition table when the macro is defined. So we shall see the data structures, namely the name table and definition table that is created for this macro definition. Statements from line number 30 to 95 would be saved into the definition table. The name of the macro, that is rdbuff, would be added into the name table. And as I mentioned, comment lines are ignored. All parameters would be replaced with positional notations. So every occurrence of I and DAV would be replaced with question mark 1. Occurrence of buffer address would be replaced with question mark 2. And record length would be replaced with question mark 3. So you may see the data structures here. Name table contains the name of the macro rdbuff. The prototype, that is name and parameters, appears as a first line in the definition table. Following that, statements from clearx to amend are entered and 2 pointers are set to the beginning and end of the macro definition. All occurrences of inrep is replaced with question mark 1, buffer address with question mark 2, and record length with question mark 3. The macro invocation appears in line number 190. And you see that opcode field contains the name of the macro rdbuff, which is also an entry in the name table. So this identifies a macro invocation statement, and the arguments that follow are f1, buffer, and length, which has to be substituted for the first, second, and third parameters respectively. So the argument table setup is shown here. The first argument is entered first, followed by buffer, followed by length. The first entry in the argument table is f1, which is to be replaced for the positional notation question mark 1. The second entry buffer would be replaced for question mark 2, and the third entry length would be replaced for question mark 3. We are now ready to look into the algorithm for the one-pass macroprocessor. A one-pass macroprocessor requires that macro definitions appears in the source program before the macro invocations. That is, macros must be defined before they are called. The main algorithm or main procedure makes use of 4 sub-procedures, namely define, expand, getLine, and processLine. Function of the define procedure is to define the macros. And generally this procedure is called or invoked when a macro definition is encountered in the source file, which happens when the directive macro is encountered. So the define procedure makes entries into the definition table by storing the prototype and statements that form the body of the macro. Name is entered into the name table. The function of the procedure expand is to expand a macro invocation statement, and the procedure is invoked whenever the opcode field contains a macro name that is also an entry in the name table. So the procedure expand sets up the argument table and expands the macro invocation statement by replacing it with statements that form the body of the corresponding macro. The function of the getLine procedure is to get the next line that is to be processed. Next line that is to be processed can come either from the input file or from the definition table. So there are 2 sources, so which is actually controlled using a variable, namely expanding. If expanding is true line would be read from the definition table, otherwise lines would be read from the input file. Function of the process line procedure is to process every line that is read by the getLine procedure. So we will look into detail each of these procedures, beginning with the procedure define. As I mentioned, the procedure define is called when the beginning of a macro definition is encountered, which is nothing but the directive macro. The define procedure makes entries into the two data structures, namely definition table and the name table. It enters a macro prototype and statements that form the body of the macro into the definition table. And the name of the macro, which appears in the symbol field, in the label field, are entered into the name table. Further, the name table holds two pointers to the beginning and end of the macro definition that is saved in the definition table. The figure below depicts the use of defined procedure in macro processing, and as you see, the procedure is being invoked by the process line procedure. And when is it invoked? It is invoked when the opcode field contains, or when the statement that is processed has the macro directive in the opcode field. So when the opcode is macro, the procedure define is invoked, and the procedure define uses two data structures, that is name table and the definition table. The name of the macro is entered into the name table and the definition is stored or saved in the definition table. As I mentioned, the prototype appears as a first line, and following that, statements that form the body of the macro are entered into the definition table with all parameters replaced with positional notation. The name table holds two pointers to the beginning and end of the definition in the definition table. Expand procedure is used to help in expanding a macro, and the function of the expand procedure is to set up the argument table by placing all arguments that are encountered in the macro call into the argument table in the order of their position. So the figure below depicts the use of expand procedure in macro processing, and as with the define procedure, the expand procedure is invoked by the process line procedure, and this happens when the opcode field contains a macro name that is already saved in the name table. So the presence of a macro name in the opcode field, which is also an entry in the name table, indicates a macro invocation statement. Expand procedure uses two data structures, that is a definition table and argument table. Argument table is set up when a macro invocation statement is encountered, that is the procedure expand sets up is used. First thing that the procedure expand does is it sets up the argument table by placing the arguments that follow the macro name in the macro invocation statement into the argument table. Also, the definition table is used to fetch the lines that have to be used as a part of macro expansion. That is, macro invocation statement has to be replaced with statements from the body of the macro that is saved in the definition table. Function of the getLine procedure is depicted in this figure. As you see, the getLine procedure examines a variable expanding to see if it is set to true or false. So if expanding is false, the next line that is to be processed is fetched from the source program or from the input file which has macros. While if expanding is false, the lines will be read from the definition table instead of from the source file. Because expanding is true means that you are currently expanding a macro, in which case the stored macro definitions needs to be fetched from the definition table. The relationship between various procedures are shown in this particular slide. The main program iteratively calls the procedure getLine and processLine, whose function is to fetch the next line and accordingly process it. The iterations end when the end of the source program is reached. That is, when the opcode is end, the process ends. You may see the getLine procedure gets the next line, but it is depending on the value of the variable expanding. If expanding is false, line will be read from the input file, while if it is true, the next line that is fetched is from the definition table. The process line procedures function is to process every line that is being fetched by the getLine procedure. So it performs examines three things. First is it checks if the opcode field is a macro directive, which means it is a beginning of a macro definition, in which case the define procedure is invoked. If the opcode is not a macro directive, it searches the opcode in the name table to see if it is a macro name which is already saved in the name table. In other words, a name would appear in the name table only if the macro definition would have been encountered earlier. So if the process line procedure finds the name of a macro in the name table that appears as a opcode for the instruction that is currently processed, then it calls the procedure expand because the statement indicates a macro invocation. If it is neither if the opcode neither indicates a macro directive nor it indicates a macro name that is present in the name table, then it simply places the line to the expanded file without further processing. The function of the define procedure, as I mentioned earlier, is to make entries into the definition table and name table for saving the macro definition and the macro name. Prototype and statements that form the body of the macro with parameters replaced with positional notation would be entered into the definition table. Macro name would be entered into the name table with pointers to the beginning and end of the definition in the definition table. The function expand, as mentioned, is used to aid in the macro expansion. So first thing that is done is setting up of the argument table, wherein all arguments in the macro invocation statement are saved, and the macro invocation statement itself is written as a comment line to the expanded file. And next, it iteratively calls two procedures getLine and processLine to fetch the next line. And at this point, the getLine procedure examines the expanding variable and it fetches a line from the definition table as if the expanding is set to true. The first thing that is done in the expand procedure is to set expanding to true so that lines will not be now read from the definition from the input file but from the definition table. So as each line is fetched by the getLine procedure, it will substitute the positional notations with arguments, and statements would be generated as a part of the expanded file. One point that needs attention here is handling of nested macros, that is one macro definition enclosed within the outer definition. We call such macros as nested macro definitions. So when a macro definition is entered into a definition table, generally the approach is to go on saving the definitions till mn directive is encountered. So if one macro definition is nested inside of the other macro, when amend is encountered, there is a possibility that the amend would be misinterpreted as the end of the macro definition of the outer macro. So in order to handle definitions of one macro within another, a special variable, namely level, is used. So consider this example. This is a macro written for the SIC machine, which includes the definitions for reading the records and writing the records. The outer macro is named macro S, which is not having any parameters, and it includes definitions of two macros, namely rdbuff and wrbuff. The amend at line 3 corresponds to the end of the macro rdbuff, Mend at line 5 indicates the end of macro WRBUF, and the mend at the line 6 actually corresponds to the mend of the outermost macro. During the saving of macro into the definition table, normally statements that form the body of the macro would be entered until mend is reached. So the mend at line 3 should not be interpreted as as an end of the macro definition for macro S. So in order to handle this, a counter or a variable namely level is used to keep track of the levels of macro definitions. Mend is interpreted as end of a macro that is currently being processed only when level reaches 0. That is, in other words, whenever we see a macro directive, level is increased by 1, and whenever mn directive is read, level is decremented by 1. So mn will terminate the macro definition process only when level reaches 0. So this process is very much like matching of the parenthesis, left parenthesis and right parenthesis when arithmetic expressions are processed. So consider this nested macro. We have the outermost macro, namely macro S, and it incorporates the body of the macro S includes two macros being defined. One is rdbuff and wrbuff, which includes instructions for SIC machine with respect to rdbuff and the macro wrbuff. We shall see how the variable level helps in handling macro definitions that are enclosed within outer macros. So initially we have name tables and definition tables which are empty. So we begin by processing the statements one after the other, starting from line number 1. So the first line here is macro S, macro, which identifies the beginning of a macro, namely macro S, because opcode has the directive macro. So when this statement is encountered, since this is the beginning of a macro definition, as usual, prototype will be entered into the definition table and name is entered into the name table. So the macro name here is a symbol in the operand field, which is macro S, which has been entered into the name table. The prototype includes only name because the outer macro doesn't have any parameters. So the prototype includes only the macro name, which has been entered as a first line into the definition table. And the name table holds pointer to the beginning of the macro S. Since the directive is macro, level is set to 1 at this point. Whenever a macro is encountered, we increment the level by 1. So initially, when the first macro directive is encountered, level is set to 1. Next, we proceed ahead with the processing of the next statement. The next statement here is the statement rdbuff macro ampersand indv buffer address and record len. This is the second line as you see here, and it is the first line of that forms the body of the outer macro S. So when this line is processed, since the opcode here is a macro, it again indicates the beginning of a new macro. So the current line is entered into the definition table with the prototype, and the name of the macro rdbuff is entered into the name table. So you may see that rdbuff has been entered into the name table. The prototype for the second macro definition rdbuff is entered. Rdbuff along with parameters is entered into the definition table. Also, since the directive here is macro, level is incremented by 1. So level is right now it is 2. Also, you may see that rdbuff holds a pointer to the beginning of the macro definition rdbuff in the definition table. The processing of statements is next continued. The following statements are dotted lines indicating the part of the body of the macro rdbuff. So as you see, since this represents body of the macro, they are entered into the definition table. we are not yet encountered the end statement, or the level has not yet reached 0. So execution will proceed ahead, and the next statement is fetched, which is amend. So when amend is encountered, it indicates the end of a particular macro definition. However, please note this amend does not correspond to end of the outer macro, and this is indicated with the level here. Earlier, level was 2. Now when amend is encountered, we decrement the level. Every time macro is seen, level is incremented. Every time amend is seen, level is decremented. So at this point, we decrement the level by 1, and that is why we have the level set to 0. So since level is not at 0, we continue ahead with the processing, and the next statement taken is wrbuff macro out diff buffer address and record length, shown in line 4. Now the opcode here is macro, which again indicates the beginning of a macro definition. So the name of the macro is entered into the name table, and the prototype is entered into the definition table. Prototype is name of the macro wrbuff and the parameters. There are 3 parameters: outdiff, buffer address, and record length. Since the directive is macro, we increment the level by 1. Earlier the level was 1, now level is 1 plus 1, which is 2. Next, we proceed ahead with the next set of statements, which is dotted lines, which are shown here. So there is no change with the level, and we have not yet reached a level equal to 0, so we can continue ahead with the processing of macro definition. The next statement encountered is amend. So this indicates the end of a macro definition. So when this amend is reached, level will be decremented by 1, and so now level is 1. Since this indicates the end of a macro definition, that we were currently processing, pointer is set to mark the end of the macro definition, and the execution proceeds ahead with the remaining set of statements that form the body of the outermost macro. Please note we have come to the end of 2 inner macros, the rdbuff and wrbuff. At line number 5, we find the amend for the second macro that is wrbuff, that is contained within the outer macro s. So at this point, the remaining statements are entered into the definition table, and the next statement is taken for execution because level is not at 0. So the next statement encountered is amend, which is entered into the definition table. Since it indicates the end of the definition, pointers are accordingly set. Also, level is decremented by 1, which causes it to be set to 0. Since we have reached 0 now, it means that the end of the outermost macro has been encountered. So we are done with the processing of the outermost macro, and you have seen how level counter or variable could be used to handle the definition of nested macros, or one macro definitions enclosed within another without any problem. So we shall now discuss the algorithm for one pass macroprocessor. The main macroprocessor algorithm is shown first, which repeatedly invokes 2 procedures, namely getLine and processLine, until the end of the macroprocessor is reached. Initially, the variable expanding is set to false, which enables lines to be read from the input file rather than from the definition table. As I mentioned earlier, the function of getLine procedure is to get the next line. So the getLine procedure examines the variable expanding, and if it is set to false, it reads the line from the input file. While if expanding is true, it fetches the next line not from the input file but from the definition table. And as a line is fetched from the definition table, it examines if the line that is currently being fetched has a parameter or a positional notation. So if the line that is currently fetched from the definition table has a positional notation, it will be replaced with the arguments from the argument table. So the function of getLine procedure is to fetch the next line, which could be either from the source file or from the definition table when macro expansion takes place. For every line that is fetched, process line procedure would be invoked. And the function of the process line procedure is to check if the line that is currently read is a macro directive indicating the beginning of a macro definition, or if it is a macro invocation, or if it is a source line that does not require further processing by macroprocessor, and so could be written to the expanded file. So the 3 cases are actually examined in the procedure process line. So as you see, the first statement here is search name table for opcode. So whenever the process line procedure is invoked for a particular line that is read, it examines the opcode field and sees if the opcode is a name that is already saved in the name table. So if it sees that the name opcode is a name that is in the name table, then it means that it is a macro call. So it invokes the procedure expand in such case. Now, if when the process line procedure does not find the opcode in the name table, it sees if the opcode is a macro. That is, it sees if the corresponding statement that is currently processed is an indicator of a macro definition. So this is identified with the opcode macro. So if the opcode is macro, the defined procedure is called in order to save the definitions that follows. Otherwise, if it is none of these two cases, the source line will be just copied to the expanded file without any further processing. So to summarize, process line procedure does three things. It searches the opcode in the name table. If it is found macro, it indicates a macro invocation. So expand procedure is called. On the other hand, if the opcode contains the directive macro, then it means the beginning of the macro definition. So it calls the procedure define to save the macro definitions. Otherwise, the line will be copied as such to the expanded file without further processing. The procedure define is shown here, and the function is to save the macro definition with the prototype and the name into the name table with the definition saved into the definition table. So as you see, the first line here is enter the name into the name table. So when the define procedure is called, the procedure first enters the macro name into the name table, which is generally in the label field. The symbol in the label field is entered into the name table. Macro prototype is entered into the definition table. Prototype is the name of the macro and the parameters. That is, the symbol in the label field and the parameters in the opcode in the operand field will be entered into the definition table as the first line. Also, currently, the defined procedure is invoked whenever macro directive is encountered. So at this point, since the directive is macro, level will be set to 1. So this is, as I mentioned earlier, is used to handle nested macros. So as long as the level is greater than 0 or not equal to 0, lines will be fetched one after the other using the getLine procedure. So the getLine procedure, as I mentioned earlier, examines the settings of variable expanding and accordingly fetches the lines. For every line fetched, the macroprocessor checks if the line is not a comment line, and if not, it enters the line into the definition table by substituting parameters with the positional notation. So whenever a line is entered, it also examines if the currently fetched line is again a macro definition identified by the macro directive macro. So if the opcode is a macro, it increments again the level by 1. And if the opcode is amend, it decrements the level by 1. So for every line that is fetched, the macroprocessor examines if it is a comment line. If it is a comment line, this line will be simply ignored and the next line will be fetched. If it is not a comment line, the line will be entered into the definition table with parameter replaced with positional notation. Also, for every line that is fetched, it examines if it is macro or amend, in which case it either increments or decrements depending on macro or amend. So the process is repeated as long as level is not equal to 0, and when level becomes 0, it means we have reached the end of the outermost macro, especially when we have one macro nested within another. So at this point, pointers are set in the name table to the beginning and end of definitions that are stored in the definition table. The procedure expand is used to set up the arguments and expand the macro invocation statements. First step here is to set expanding to true. This is done to make sure that lines are fetched from the definition table and not from the source file. because expansion has to do with replacing the macro call with statements that form the body, which are saved in the definition table. So lines now has to be fetched from the definition table. So after expanding is set to true, the first line will be fetched from the definition table, which is generally the macro prototype, and this first line actually corresponds or is actually identified by the pointer from the name table, because expand procedure is called whenever a name is found in the macro name is found in the name table and the corresponding definition is read. So the first definition that is read is a macro prototype corresponding to the macro name that was found in the name table. So after prototype is read, the arguments are set up in the argument table in the order of their position in the macro invocation statement, and the invocation statement itself is written as a comment. Further, the statements are fetched and processed using the getLine and processLine procedure until the end of the macro definition is not reached. Or in other words, after the prototype, one after the other lines will be fetched using the getLine procedure, and it will be processed until mn directive is encountered. When the mn directive is encountered, expanding is set to false, indicating that it is the end of the macro definition. It's the end of the macro expansion. So that hereafter the lines would not be read from the definition table but from the source file. One important aspect with respect to the use of getLine procedure within the procedure expand is that whenever getLine procedure is called within expanding would be set to true. So at this point, the line would be read from the definition table, and for every line that is fetched, if there is a positional notation, it would be replaced with arguments that are set up in the argument table by the procedure expand. So that is all with respect to the one-pass microprocessor algorithm. So to summarize, it uses 4 procedures: the get line for fetching the next line, process line for processing every line fetched, define for defining the macros, and expand procedure to expand a macro invocation statement. So we shall now compare the algorithm for one-pass microprocessor with that of two-pass. One-pass microprocessor algorithm requires that every macro is defined before it is called. In other words, in the source program, macro definitions should be present before macro invocations. And a one-pass microprocessor algorithm has advantage that it is able to alternate between macro definitions and expansion in a single pass. Also, it is able to handle macro definitions within macro definitions, what are called as nested macro definitions. However, one-pass microprocessor algorithm is not able to handle one macro call within another, or nested calls are not handled by one-pass microprocessor algorithm. On the other hand, a two-pass algorithm works by processing all macro definitions during the first pass and expanding all macro invocation statements in the second pass. A two-pass microprocessor algorithm is not able to handle macro definitions within macro definitions, because the problem is inner definitions are processed only when the outer macro is called, which happens in pass 2. So inner macros will not be defined in pass 1. So that is all with respect to the macroprocessors. We have discussed the basic concepts of microprocessing, including how to define a macro, how to expand a macro invocation statement, and how a microprocessor recognizes macro definitions and macro calls, and the basic functions, how the basic functions are accomplished using the one-pass microprocessor algorithm, and the associated data structures used, such as name table, argument table, and the definition table. Thank you.